this oxygen, based on the Lewis structure we've drawn, has a +1 formal charge. Okay? This carbon, this is an easy calculation again. No lone pairs on the carbon. 4 bonds, of which it gets half of the bonding electrons, so it gets half of 8 bonding electrons. That's 4. That's basically the same calculation that we did for this carbon up here. And so this carbon's formal charge is 0. What about that other oxygen? Anybody know the formal charge on that off the top of their heads? This oxygen right here, that's single bonded to carbon and has 3 lone pairs. We do the formal charge on that oxygen, call that oxygen number 2. 6 electrons in the neutral oxygen. You've got 6 electrons in the form of lone pairs, 3 lone pairs, 2 electrons apiece. That's 6 electrons there. Plus, you get half of the 2 electrons in that bond. So, plus 1/2 times 2. 7. 6 minus 7, -1. The formal charge on that oxygen with 3 lone pairs and a single bond is -1. This structure implies, this Lewis structure implies that electron density has moved away from this oxygen and towards this one, leaving that oxygen charge deficient and leaving this oxygen with an excess of charge. And so now we have to choose between this structure and this structure and decide which one of them is the most realistic in nature. Which one of these electron distributions is going to resemble what we actually find in nature? Well, I told you it takes energy to create a separation of charge. And so this structure here with the zeros, the 0 formal charges on all of the atoms, that guy is the one that is most likely to be found in nature. Right? This is the one that's probably most representative of the true electron density in the CO2 molecule. This guy, not so much. You're not going to get a charge separation. And so based on the evaluation of formal charges, we would select this guy as being the bad structure and this one over here as being the best structure. All right. Here's one for you. NO2F. We're going to build a molecule using a single nitrogen, 2 oxygens, and a fluorine. How many valence electrons? We've got 1 nitrogen, 5 electrons in the nitrogen, 2 oxygens, 2 times 6 electrons for the oxygen. It's 12. And we've got 1 fluorine. That'll be 1 times 7. So 7 valence electrons in that fluorine. So the total number of valence electrons that we have in this neutral molecule is 24 electrons. We need to divide up 24 electrons over all of those atoms. First thing we're going to do, establish a molecular geometry. Nitrogen is our least electronegative species, so we're going to assume that the fluorines and the oxygens kind of surround it in space as they go after its valence electrons. So we'll stick our nitrogen right there. And we'll just surround it with all of the other species. Whichever one is the least electronegative. So based on positions in the periodic table, in the first week we learned how to define which species were more and less electronegative. The least electronegative one goes in the center. We start dividing our electrons amongst the different atoms. We're just going to link all the atoms together by a single covalent bond. That spends 2, 4, 6 electrons. And so from our total, we have to subtract the 6 electrons that we just distributed as bonds. It means that we've got 18 electrons left to distribute. We start handing those electrons off to the most electronegative species first. Fluorine is the most electronegative. Start giving it lone pairs. At the point that we've given fluorine 3 lone pairs, 6 electrons, it now has a filled valence. We've got 12 electrons left to give away. Start giving them away to the oxygens. Give 6 away to this oxygen, it has its filled valence. And we give 6 away to this oxygen, and it has a filled valence. Okay? At that point, we've spent all the rest of our electrons that we had available in that molecule. And we're left to decide from this point what is the best way to give nitrogen a filled valence shell. In the structure that we have right here, both of the oxygens have filled valence shells. They've got octets, as does the fluorine. But the nitrogen only has 6 electrons in its valence shell from those 3 bonds. So that nitrogen is not electrically satisfied. We need to find a structure that shows it being electrically satisfied. And again, there might be more than one way to do this. There is, in fact, more than one way to do this. So we got to draw the different structures and weigh them based on formal charge calculations. So let's do this first. Let's build a structure, build it down here, where we've moved the lone pair from the fluorine into a bonding position to that oxygen. The fluorine will sit here. It'll now have only 2 lone pairs, and its 3rd lone pair will be now a double bond to the nitrogen, and we'll have a couple of oxygens coming off of that nitrogen. And this will be our structure. We could do it that way, but there's another way we could have done it. We could have, instead of moving fluorine's lone pairs, we could have moved the oxygen's lone pairs. We could have moved this oxygen's lone pairs or that oxygen's lone pairs. That would have given us 2 different structures that are actually kind of electrically equivalent. One would look like this. Single bond between nitrogen and the fluorine, double bond between nitrogen and one oxygen, and single bond between the nitrogen and the other oxygen. If we just move the other lone pairs from the other oxygen, our species would look like this. In all 3 of these structures, every atom type has a filled valence. The oxygens and the fluorines and the nitrogens have filled valence here, as they do here and as they do here. So again, now it's time to weigh the structures based on formal charges. I'm going to do this fast because we're running out of time. I'm hoping that you guys have plenty of time to get to practice this in your homework. This oxygen, a single bond oxygen, with 6 electrons. We already did this calculation once. It's a -1 formal charge. This oxygen right here, double bond oxygen with 2 lone pair electrons. We did that calculation earlier on another molecule. It's a 0 formal charge. Yeah? Fluorine. Fluorine normally comes with 7 electrons in its valence shell. We've got 6 lone pair electrons plus half of 2 bonding pair electrons. That's 7 electrons. This fluorine has a 0 formal charge. What were you getting at here?
I was going to ask about nitrogen. How many spots does it have?
Nitrogen has 5 valence electrons. It has room for 3. But we kind of throw that out the door when we start doing Lewis structures. When we do Lewis structures, we don't assume that they're going to want to gain 3 electrons. We just assume that the electrons are going to be distributed based on electronegativity, and the atoms will end up with what they get. Whatever that is.
Don't really care about nitrogen.
Don't think of it in terms of, oh, nitrogen wants to gain 3 electrons or oxygen wants to gain 3 electrons. Think of it in terms of, I got a handful of electrons and I got a handful of atoms, and I'm going to start giving those electrons away preferentially to the most electronegative atoms. And then I'm going to look at what structure I come up with. Okay, so I did this fast. Nitrogen, 5 valence electrons. So we'll do the formal charge of the nitrogen here. So got 5 valence electrons. We're going to subtract from that half of 8 bonding electrons. So that's 4. So minus 4 is plus 1. That nitrogen right here has a plus 1 formal charge in that species. All right? Now, I did that really fast without mapping out all of the formal charge calculations. We'll run out of time, so I don't have time to do it slow. This oxygen, again, 3 lone pairs, a single bond, that's a minus 1 formal charge. This oxygen right here, 3 lone pairs, single bond, that's a minus 1 formal charge. This nitrogen right here, 5 valence electrons, 4 in the form of bonding electrons, that is a plus 1 formal charge. And this fluorine, in this atom, or in this molecule, normally comes with 7. It's got 4 in the form of lone pairs, plus half of 4 bonding electrons, that's 6. So this Lewis structure shows the fluorine with 1 fewer electron than it normally comes with. That is a plus 1 formal charge. All right? Now, this molecule over here is just kind of the inverse of that one, so we can transfer those those formal charges. -1 here, 0 on the fluorine, 0 on that oxygen, and plus 1 on that nitrogen. 3 different structures. All of them satisfy the octets of the different atoms involved. The question is, which of these structures is most representative of the true electron density in the molecule? We're going to go to formal charge. Notice that this species has a couple of problems here. This guy in the center. I've got a positive charge sitting over here on the nitrogen, separated from positive charge sitting over there on the fluorine, separated from a negative charge sitting on this oxygen, separated from a negative charge sitting on that oxygen. Basically, I've taken a lot of differently charged particles and I've spread them out in space. I've moved positive charge and negative charge further away from each other. This structure is high in energy. It's probably not very likely to be the true structure of the molecule. Right? Nature doesn't like to go to high energy. You give nature a chance, it'll take a low energy arrangement. And so this guy right here, just the fact that you got so many different charged atoms makes it highly unlikely that this guy is the true structure or is a good structure. This structure has one more problem. I'm showing over here in this structure a plus formal charge on a fluorine and a negative formal charge on an oxygen. Which one's more electronegative, fluorine or oxygen? Fluorine. So which of those atoms would be most likely to gain the electron in the electron tug of war? Fluorine. But I'm showing fluorine as being positive and not negative. That doesn't make sense. Fluorine's going to win an electron tug of war. You're not going to have a positive formal charge on fluorine and a negative formal charge on an oxygen. Not very likely. Bad structure. These two structures, easy to analyze, they're equivalent. Notice that now I've got fewer charge altogether, fewer formal charge. Back here I had 4 different charged atoms. Here I've only got 2 different charged atoms. I've got my nitrogen and one of my oxygens that are charged. Notice also that the charges are closer together. Well, they were close together in the other one. But basically I just don't have that much charge separated across the molecule in this species. That's a good thing. And also, the fact that, well, I was going to say the fact that the negative charges on the oxygen is good, but that's not exactly the truth. The truth is your fluorine can't take on a negative formal charge state without drawing more than an octet of electrons around its valence shell, and so you wouldn't end up with a species with a negative formal charge on the fluorine. Does that make sense? What time is it? 2:57. We got 3 minutes left. It's probably not enough time for another one. Maybe it is time for another one. Let's do one more real quick. All right? It's going to be fast. Somebody told me you guys don't understand anything I say, so I'm just going to say it more often. Real quick. We're going to build M2O, all right? M2O. Each nitrogen's got 5 valence electrons, oxygen's got 6. So we got 16 electrons that we're going to give away. With this one, nitrogen's the least electronegative, so we'll stick it in the center, or one of them in the center. We'll stick the other one in the peripheral. We'll draw single bonds between all of the atoms, linking them together. That's 4 electrons that we spent. We've got 12 electrons left. We're going to start distributing them to the peripheral atoms. Stick these guys here, these guys here. At that point, this nitrogen has a filled octet, this guy has a filled octet, and now we've spent the last 12 electrons. We've got 0 valence electrons left that we have to distribute. And next step is to try to make sure that this nitrogen has a filled valence. Again, we could start moving lone pairs from the oxygens in towards the nitrogens, or we could move lone pairs from this nitrogen in towards that nitrogen. Now, for sake of time, I'm going to skip the next couple steps, but after you've started moving these lone pairs around, you'll get 2 possible scenarios for Lewis structures. You could end up with this guy here. In this case, you've got a 0 formal charge on this nitrogen, you've got a +1 formal charge on that nitrogen, and you've got a -1 formal charge on this oxygen. Check yourselves. In the other possible structure, you could end up with a Lewis structure that looks like this. Where you've got a positive formal charge on this nitrogen that has 4 bonds to it, a 0 formal charge on that oxygen, and a -1 formal charge on that nitrogen. Notice that this nitrogen has 2 lone pairs, 2 bonds to it. This nitrogen in the center always has 4 bonds in either structure, and this nitrogen here has a single lone pair and half of 3 bonds, so half of 6 bonding electrons. Which structure is better? Anybody tell? Which species is most electronegative, oxygen or nitrogen? And so if you're going to draw a Lewis structure with negative formal charge on it, which atom does that formal charge belong to? Oxygen. Negative formal charge always goes to the most electronegative species. And so this structure over here, it shows the negative formal charge on the oxygen, and it shows a positive formal charge on the nitrogen. Note that the sum of the formal charges will always equal the charge on your molecule. We've done all neutral molecules in class today, so the sum of all our formal charges have always had 0. And here, they're 0 as well. 1 + 1 on the nitrogen, -1 on the oxygen. Compared to over here, we've got a negative charge on the nitrogen, on this nitrogen, a positive charge on that nitrogen, and a 0 charge on that oxygen. This structure is not like what you're going to find in nature. It's not very representative of true electron density. This structure is a better structure because it shows the negative formal charge on the more electronegative atom. Okay? Practice makes perfect. Let me say something. I did that thing where I didn't give you guys deadlines on the homework. That is acting to hurt some of you. Some of you guys have not opened your homeworks. You haven't prepared for exams using homeworks. You've got to start cracking through those homeworks. That's where you get your practice. You're not going to get it just by listening to me say it, and you're not going to get it just by studying the study exam for the test. You've got to do some of those homeworks. If you don't practice it, you won't know it.